Okay, so let's start by recapping what happened yesterday. Okay, so we started with this motivating example, Arab's theorem, what you need to do to get a Nobel Prize in economics, sorry, the economics prize of the Norwegian, whatever. And we discussed, so this Arab's theorem says that in some sort of elections, the only way to aggregate the votes so that you always get an actual ranking on 3 candidates is if you choose somebody and they get to decide. And we don't like that, so we ask, okay, let's say everybody votes randomly because otherwise everything trivializes and we know in advance who's going to win. So let's say everybody votes completely at random. Maybe now there's a way to escape the paradox by allowing a small error, small chance of mistake. And it turns out that this is not the case. Okay, so how does all this relate to Boolean functions? So it turns out that you can, so this, just to remind you, this social choice function that we're considering is a Boolean function. It gets the opinions of all the voters on who do they prefer among 2 specific candidates, and it outputs the aggregated preference. And it turns out that for this function to work out, it has to have degree 1. And because it's odd, then the only degree 1 odd functions are dictators and anti-dictators. So you just copy one of the coordinates, or maybe you flip it. And if this function works with probability 99%, then it's 98% close to degree 1, whatever that means. And I'll explain what it means, and I'll write it out shortly. And then this FKN theorem states that it has to be close to a dictator. Okay, so again, so yesterday we worked with plus minus 1. Now we're going to switch to 0, 1, just to confuse you, and because it's more common to do so when working over a bias domain. So suppose this is the FKN theorem. This is the know. So suppose f is a function from 0, 1 to the n to 0, 1. And suppose that it satisfies f greater than 1 squared is epsilon. Okay, so just to remind you, that we use capital. So f greater than 1, this is as follows. So we go over all the Fourier coefficients size larger than 1, and we take the Fourier coefficient times the character, where the character in this case is minus 1 to the sum f of xi. Okay, so this is like these F2 polynomials that we saw in the previous talk. Okay? Then F is order epsilon close to Boolean 1 function. So a function depending on at most 1 coordinate. So it could be constant or it can be a dictator or an anti-dictator. Okay, so we can make a list of these functions. These are 0, 1, xi, 1 minus xi. Okay, so that's what we saw yesterday, and the proof, we first classified the Fourier coefficients small and big, and we said that at most 1 can be big just by considering the Plancherel inequality, or Parseval identity, whatever you want to call it. We reduced the case where one of them is strong to the case where all of them are very small, just by substituting all possible values. And then we said, okay, if all of these Fourier coefficients are small, then the distribution is kind of Gaussian, and the only way in which a Gaussian can be always close to, let's say, an average close to plus minus 1 is if it's essentially concentrated, like it has small variance and it's concentrated around one of these values. And this is really the statement of the FKN theorem. Yeah, so now I should replace plus minus 1 by 0. And technically, we use the Berry-Essen theorem, which can be proved using some sort of induction. There are also, you can hide this induction inside the sum if you want, and then you don't have any induction. There are several different proofs of this FKN theorem, and in some sense, they're all similar. They just put the induction in a different step of the proof. So, like the more direct inductive proofs are like in Geistis or in Christoph's paper and so on. In the original paper, they have this proof based on hypercontractivity, which is like the proof I showed, but instead of looking at the CDF, you look at some L2 or L4 norm or something, and you do it the same. Okay, so this is the FKN theorem. And we also discussed, okay, so we started with some actual motivation, and this was this quantitative version of Ayres' theorem was the actual motivation for this result. So I think in the paper, you asked, okay, so what can we say about such functions? And then it was answered in this paper. And now we're going to take this theorem and go forward and ask similar questions, which are maybe the motivation is not as great. Okay, it's not completely absent, but it's not as great. So essentially, we can take it into two different directions, and we'll pursue one direction first and the other direction later. So the direction we're going to pursue later is instead of looking at degree 1, we're looking at some degree d, where d is constant. Okay, so this actually arises in extreme combinatorics. Yeah, I think by now it's like a fake example because we know better ways of doing everything. But back then, maybe it wasn't so fake. And the other thing which we consider, this is what we're going to do today, and it's actually related because you have to do both, is where you look at different domains. Okay, so for us, a domain is both a set, like the actual domain of the functions, and also a probability distribution over this domain. So it comes together. It's really a probability space. Okay, so we saw some different probability spaces this morning and also yesterday. My favorite domain is a symmetric function, which we hopefully will see tomorrow. If you make it, it's a bit early. But today we're going to start with a warm-up example, which is the P bias cube, which was also mentioned by Noah. Okay, so today we're going to ask, what happens if we endow 0, 1 to the n with the measure mu p. Okay, and the measure mu p, so if you think of 0, 1 to the n as this collection of subsets of numbers 1 up to n, then the way to sample a mu p set is by putting it each element with probability p. So the probability that xi is equal to 1 is p, and otherwise it's a product distribution. Okay, and this defines the measure. Sometimes we work with different marginals, and you can do it and nothing really changes, but the typical case is where all of the biases are the same. Okay? And now there are sort of two regimes. One regime is when p is not a half, which is what we've considered up to now, but it's maybe a third, some constant, something which is bounded away from 0 and 1. And then in most cases, it just behaves the same, like in general in Boolean function analysis. So if you have a result for mu half, usually it also holds for mu p with for any constant p. Not always, but usually. Yeah. And this is also the case here. Okay, so suppose p is any constant. And we can repeat the proof. and get the FKN theorem with an error bound of OP of epsilon. Or we can compute this dependence on P. I don't know if it's optimal, but so you literally repeat the same proof, and I'll tell you what you need to change. So the first part, we looked at this Laplacian, and we use the fact that it's 0 plus minus 1. So now we need to change it with this differential operator that Nom defined. Okay, so we have to change it. So instead of LIF, we look at VIF, which is defined like this. Okay, this is just some technicality. Okay. And the other thing, so when we were doing this approximation by Gaussian, then the error term involved the ratio between the third moment and the second moment of something. Okay. So when we're doing Fourier analysis with respect to this p-bias measure mu p, then we need to work with the Fourier basis, which is orthogonal with respect to the p-biased inner product, where we take the expectation over mu p. And Nom actually, he already wrote what the Fourier basis is like. So before this, the Fourier basis looks like this. Okay, so these are the basis functions. So this number, this is the expectation of xi, and this is the standard deviation of xi. Okay, so we normalize it so it has mean 0 and variance 1. Okay, and this is what ensures that this is actually going to be orthonormal with respect to this mu p measure. Okay, and now when we do this normal approximation, then this is no longer plus minus 1. So we need to compute the ratio of the absolute third moment divided by the second moment. Now the second moment is, by construction, it's 1. Okay, so we just need to compute this thing. And this turns out to be something like 1 over square root of p 1 minus p. Okay, you just have to trust me. But it's a straightforward calculation. This is going to be the error. So the error in the quantitative central limit theorem, the very essence theorem, is going to be proportional to this thing. And you can see that this blows up when p gets closer to 0 or to 1. But as long as p is constant, then this is just some other constant, which is going to figure out into this constant. Okay, so if we change the bias from 1/2 to 1/3, then everything still works. Okay, we needed to do this extra calculation to make sure that really everything still works, but otherwise it's all the same. Okay, there are some results where it's not true. When p is equal to 1/2, then these characters, they have this property that if you take xs times xt, then you get x of s XOR t. And it's a group, right? The characters form a group. And this is no longer the case here. Then sometimes it's important that they form a group, and then we're kind of screwed. If this is a property that we're supposed to use, and now we move to a different p, and then you need to use something else. Okay, but it's not the typical case. Okay, so this is about constant p, which is different from 1/2. Okay, so questions about that? Yes.
So then your Fourier basis, that's the one word is not longer Boolean. And how is your theorem?
Yeah, so the word Boolean is used here in two different senses. The domain is the Boolean hypercube, or the Boolean cube, and the range is often Boolean.
Right.
But here, when you're saying Boolean, then we only look at the domain.
I mean, the value is no longer 1, 0.
Yeah, but that's fine.
So then, what's at the end you're approximating?
Yeah, so it's not going to be the problem. So what we want to do is, so we classified the Fourier coefficients into small and large. And let's say we're in the case where all of the Fourier coefficients are small. Then we essentially want to state that our function is constant. It's very close to constant. And then because our function is also close to Boolean, then it's going to be close to a Boolean constant. But it's not an issue. And as an exercise, let's say that instead of a Boolean function, we look at a function whose range is 0, 1, 2. So now the FKN theorem will state that you depend on at most, I think, 2 coordinates, and you're essentially, like, you can work out all the possibilities. And the proof will be essentially the same. You're reduced to the case where the function is supposed to be constant, and so there's nothing sacred about the range here. As long as it's any finite set, everything will just work out. Yeah, any more questions? Okay. So now let's see what happens when p is close to 0 or 1. So we always consider the case when p is close to 0. Okay, so from now on, we're always going to assume that p is at most 1/2. Okay, so I'm going to write it here. Okay, so what happens when p is little of 1? Okay, and this means that we're really looking for statements where there's some n in the background which is going to infinity, and p is going to 0 together with n. Okay, it's very confusing for undergraduates. You're all like beyond this stage, so for you to be fine. Like we often discuss, we say that there exists a function, we actually mean a sequence of functions. Unless you work in non-standard analysis, then it's kind of a cheat. But you can, like, if you do it non-standard, it's fine. Okay, so the proof that we just gave doesn't work. This is related to what Noah was talking about. So hyperconductivity fails for small p. There are ways to go around it. Like you can use global hyperconductivity, and it probably gives a proof of this biased FKN theorem, maybe with potentially with suboptimal dependence on parameters. I don't know. But anyway, yeah. So the proof doesn't work, but maybe the statement is still correct. It can happen. So here's an example. So let's take the function f, which is the maximum between x1 and x2, which is also x1 plus x2 minus x1 x2. Okay, so this function is quite close to degree 1 because it's close to the degree 1 function x1 plus x2. Okay, so f is p squared close to degree 1. It's actually probably even better. Okay, but is f p close to one of these functions? Sorry, is f p squared close to one of these functions? No. So you can check, but let's say we try to approximate it by just the function x1. And the probability of mistake is like p times 1 minus p. Okay, so f is omega p r from 1 punta. Okay, so like the statement just is no longer correct. Okay, this is related to the example that Noam discussed. Okay, so I gave you an example of a function where for epsilon equal to p squared, it's epsilon close to degree 1, but it's not epsilon close to any one junta. Okay, so the FKN theorem, as stated, doesn't hold. Okay, so but here's what does hold. So this is the bias FKN theorem. Which has been used in some paper. Like there's at least one citation, so it's not completely useless. So suppose f is a function from 0, 1 to the n of the t, 0, 1, where t is small to half. And this is not important, but otherwise I'll have to have p-type moments p in many places. So, and f larger than 1 squared is epsilon. Okay, then f or 1 minus f is order epsilon close to the maximum of n coordinates where m is at most 1 or m is order of square root epsilon over p. Right? And we'll see in a moment why we get this square root epsilon over p. Just easy corollary. F is order square root epsilon close to 1 junta. Okay, just let's start with the corollary. So if m is at most 1, then it's order epsilon close to 1 junta. And otherwise, in this case, it's just order square root epsilon close to the 0 function. Okay, so we can even, it's even, I guess, slightly better. So it's either order epsilon close to a junta or a dictator, or it's square root epsilon close to a constant. Okay, so if you're, yeah.
First of all, I don't understand why there are separate cases for n smaller.
You can take just a maximum if you want.
Okay.
Okay, so if you don't care so much about powers of epsilon, you're willing to lose the power of epsilon, then you can recover the FKN theorem. It's still correct. You just have to pay this power of epsilon, which we, I guess, typically don't care about. But if you want the result to be mathematically interesting, and it will be quite mathematically interesting when we discuss other cases, then you get this more exciting structure.
That's a big O, right? Not a little O.
Yeah, yeah. That's big O. Okay, so anybody has any idea why this square root epsilon over p? So let's say, yeah, explain it. So let's, instead of looking at the maximum, we look at the sum. Okay, so consider f, which is x1 plus xc over p, and we think of c of p as very small. Okay, so what is this distributed like? Okay. So this is roughly what's on C. So the probability that f is not Boolean is going to be beta of c squared. Okay, and yeah, it's not because we have the formulas. Okay, and if c squared is epsilon, then c is squared epsilon. Okay, so this is where it's coming from. Like if m is too big, then this thing won't be close to degree 1. Okay, so in the rest of today, I'm hoping to give you maybe not a complete proof, but let's see when we have to start. That's my work. So that's funny because actually my goal was to prove an F-K theorem for the slice. So it's when you fix the Hamming weight, like the number of ones, and then you can derive this by some going to infinity. But actually, you should start with this result and then do it on the. But I'm actually not going to present the original proof, even though it's simpler than what I'm going to present, but it's less conceptual. Yeah, I discussed this with Doe, and he said, no, you should present that approach. And, yeah. So I'm following the instructions of the organizer. Think about questions to ask while I erase the board using the new technique I was taught. Let's see if I can pull it off. Yeah, any questions about the statement? Okay, so here's the main idea of the proof. So this is the main idea of the proof. P is 2p times 1/2. Okay, this is like in one word, and now we'll do it in one sentence. So you can sample x according to mu p as follows. So sample s according to mu 2p. Okay, I think of S as a set, but like we're identifying subsets with 0, 1 to the n. Okay, and 0 out coordinates outside of S. And now you sample x according to 0, 1 to the S with respect to the uniform distribution. Okay, so let's go over it again. We first sample a set S where we put in each guy with probability 2p, and we just zero out everything else. So we restrict the domain by zeroing out some of the coordinates. And then we just sample in an unbiased way the remaining coordinates. So you can check that now each coordinate is equal to 1 with probability exactly p, and everything is still independent. So we got mu p. Yeah, and this worked out because p is 2p times 1/2.
So when you say sample S, you mean you With a random S.
Yeah, so I put in each coordinate inside S with probability 2p. So for this one in P, it mostly have.
So you choose it or not choose coordinate.
Yeah, you can think of it as choosing y according to mu 2p and z according to mu 1/2, and then just taking the product of the two.
Same thing, yeah. Yeah, so far it's not very deep. You can do it even in grade school. Or, you know, they say in Russia, this you learn in first grade, and then in second grade you do integral. I don't know if it's like this still.
Unfortunately.
Okay, now why is this useful? Because we know the FKN theorem for mu half. Yes, and we can use this to do a reduction. Okay, so the starting point is the function f from 0, 1 to the n to 0, 1, such that f greater than 1 according to mu p is epsilon. Okay, now for every s, capital N, you can restrict f to 0, 1, f by just zeroing out the remaining coordinates. Yeah? Okay, so f restricted to s is a function from 0, 1 to the s to 0, 1. Okay? Now if you define epsilon s to be the distance of fs from degree 1 according to the unbiased measure, then the expectation when s goes according to mu 2p of epsilon s is most epsilon. Okay, I mean, let's forget about technicalities for a moment. So we start with the function which is close to degree 1. So if you look at the restrictions, then they're also close to degree 1 on average. And to actually make it work, you need the distributions to match up. And the way that you prove this, then you take the function which is closest to f, and you look at the restrictions of this function. And if you actually chose the restrictions of just this function, then you would get exactly epsilon. But maybe it's not the best function for the restriction, that's why it could go down. Okay, so f larger than 1 is small, so this means that if you approximate f by f at most 1, then the error is epsilon. Now if you look at the expected distance between fs and fs at most 1, then this will be epsilon exactly, because of this property. Okay, and this shows that on average, these functions are close to degree 1. So they're Boolean functions which are close to degree 1. Okay, now we apply the FKN, Yuval FKN theorem to get one quantized GS, such that f restricted to s is order Boolean. Is order epsilon s close to f restricted to s. Okay, so now I can apply the FKN theorem, the unbiased FKN theorem, which we saw last time, and approximate each of these pieces by a constant or a dictator. Okay, and now suppose all GS where the frequent of some function g from 0, 1 to the n to r. Oh, I think to 0, 1. Okay, and then it would follow that f is order epsilon close to g. So suppose that all of these local approximators GS, they all came from the same mother function. Then this mother function will have to be close to f, which is what we wanted to show. Okay, of course, it doesn't make sense because it's not going to happen if you look at the structures that we actually get. But this is sort of what we're aiming at. We want to say that these functions GS are not arbitrary, they have to match. So they have to match, and you should be able to somehow paste them together to some global function. Okay, so this is the idea. Okay, any questions? Okay, so the way that we're going to paste these things together is we're going to associate each of these functions GS with its monomial expansion. Okay, this is not the Fourier expansion. I think here it maybe not so important, but in some of the generalizations it does become important. So you can write each GS in the following way. So it's C0 plus some of I in S, Ci xi. Now the xi's are 0, 1, so this is not the Fourier expansion. Now the Fourier expansion would give you minus 1 to the xi. It's not a big difference, but it is more convenient. And we're going to associate this GS with a function gamma S, which is, it takes the set S and point 0, and it outputs to 0 plus minus 1, which takes I to Ci.
Sorry, what? GS you write as C0 plus some CI xi, but
Yeah.
CI is either 0 or 1. And there's only one, and also there's only one of them that's not.
Right. So this function is one of the following functions. Yeah, so actually the first coordinate is always going to be 0 or 1, and the rest are 0, 1, or plus minus 1, depending on the first one. And we're going to just associate it with this vector completely syntactically. Okay? And now the idea we will show that there exists gamma from n to 0 to 0 plus minus 1 such that if you take random s, then the restriction of gamma to S is equal to gamma S. Or rather, I want to state it differently. So gamma S is equal to the restriction of gamma to S with probability 1 minus order epsilon. Okay, so the way I'm going to paste these functions G together is by pasting these coefficient vectors together. And we're going to see later, hopefully today, how this is done. Okay? Okay, now suppose without loss of generality that gamma of 0 so gamma of 0 is going to be either 0 or 1. Let's say it's 0. Okay, otherwise, I just there's the theorem, but otherwise we're looking at 1 minus the function. Okay, so I'm going to define the function G as follows. So G is the maximum of xi such that gamma I is equal to 1. Okay, and I'm going to call the set of these i's J. So J is going to be the set of I such that gamma of I is equal to 1. Okay? And the idea is, or the observation, if gamma S is equal to gamma restricted to S, then GS is a restriction of G to S. Yes, maybe it's a bit confusing. But when gamma S is equal to gamma restricted to S, then this means that the set S, I mean, this can only happen if the intersection between S and J is at most 1 coordinate. And either it's 0 coordinates, in which case this function, this gamma restricted to S is just all 0, and then GS is just a 0 function. And if it's 1 coordinate, then I'm going to see a dictator. But this is just like the same thing. Okay, it's like an economic, essentially. So gamma S being the same as the restriction of gamma to S is the same as GS going to be the restriction of G to S. It may be a bit confusing, but yeah, it's confusing or convincing, or something in the middle. Okay, so so gamma S is equal to gamma restricted to S means that either S and J are joined, in which case gamma restricted to S is just a 0 function, and G restricted to S, so we zero out all the coordinates inside J, so we just get 0. Okay, or F intersect J is xi. So in this case, gamma restricted to S is at the 1 position I, and G restricted to S is xi. Then in both cases, it matches. Okay. Okay, so what does this mean? This implies, you have to do a short calculation, but this implies that F is order epsilon close to G. Okay, and why is this the case? So what's the probability that F is different from G? So the probability with respect to mu P, F is different from G, is the same as the probability, the expectation of S mu 2P that F restricted to S is different from G restricted to S. And this is at most the probability that,
What is expectation of inequality?
Sorry.
It's the expectation of the distance.
Okay, distance, right? Okay, now it makes sense. There's most probability that G restricted to S is different from GS, plus the expectation F into P. Distance between F into S and GS. Okay, but this is order epsilon and this is order epsilon, so in total it's order epsilon, right? Okay, so the only way in which these functions f and g can differ is if either GS was not the restriction of G to S, and if not, then you just take what we already know is small. And this is just maybe some technicalities. On average, GS is going to be the restriction of G, and then we know that GS and FS are close because of the FKN theorem. Okay? So we also need to explain, okay, I'll erase it, but we want to say that the size of J is small. Okay, so let's write it here. So the only way in which gamma S can be equal to the restriction of gamma to S is if the size of the intersection between S and J is at most 1. Okay, so we know that the probability that the intersection between S and J is larger than 1, this is order epsilon. Okay, and now it's a nice exercise. So this implies that J has to be either of size at most 1 or of size order of square root epsilon over P. And here S is mu 2P. Okay, I don't want to spoil the exercise for you because I have more interesting stuff to say, but you can think about it. It's not a difficult argument. It's a calculation.
Exaggeration. It's a very simple observation.
It's an observation.
Just if J is big, then the expectation of the, you need a little more than the expectation.
You need to do something, but that's elementary, and I'm not going to prove inequality. Okay, but the more interesting part is how do you show that all of these gamma S they come from this restriction of this global gamma. Okay, so that's what we're going to do. So while I erase the board, you can think if you have any questions. Yeah, any questions? No. Okay. Okay, so how are we going to prove that all of these gamma s's, they really come from some global gamma? We're going to do this using something called direct product testing, or how Yuval prefers to call it, agreement theorems. Okay? So the idea is that we're going to sample two copies of S in some correlated fashion. Yeah, so this is going to be one of our S's, S1, and this is going to be another of the S's, S2. Okay, this is intersection, and it's going to be large. Now, what we're going to claim is that with probability 1 minus order epsilon, this gamma S1 and gamma S2 agree on S1 intersect S2. Okay, and why is that going to be the case? Roughly speaking, I mean, there's some trick at some point, but so both of these functions are close to the same function f. And that's just the idea. Okay, but there is still something to do here. Okay, so this is the main idea, and now we do some of the details. So first, how do we sample these two sets? So here's one way. So how to sample two coupled copies of mu2p. So we for each I, we put I in S1 and in S2 with probability square root 2 times p. I mean, this can be any number between 1 and 2. Then we put I in S1 minus S2 with probability 2 minus square root 2p. And we put I in S2 minus S1 with probability and probability. And otherwise, I is in neither S1 or S2. Okay, this works as long as P is small enough, smaller than some constant, but that's fine because we know that the F theorem holds for constant P, so we don't care. Okay? So this middle gets like square root 2p mass, and then we chose this probabilities so that the marginals of S1 and S2 are exactly mu2p. Yeah, but otherwise, okay. And now the claim is that the probability, if you choose S1 and S2 in this way, coupled, the probability that gamma S1 restricted to S1 sec S2 is different from gamma S2 restricted to the intersection. This is order epsilon. Okay, and let's say that we somehow prove this claim. Then we apply an agreement theorem. And we get the existence of the gamma with property as above. Okay, so if we can prove that when sampled in this correlated fashion, then these gamma vectors, they typically agree, then we can somehow piece these things together. And it's not very mysterious. So the way we choose gamma at 0 is we just do majority decoding. So we choose the most popular value. And then the way we choose I, we look at all the sets S1 and S2, which both contain I, and we take the most popular value. And then you just show that it works. It follows from expansion. And yeah, I won't have time to show the proof today, but maybe tomorrow. There's some trick here if you want to not work hard. But let's say this is something that was known. Okay, so the way this proof actually came up was we started we had this idea, not of this work, but some other follow-up work, of using an agreement theorem which students of EDIT claim to know. And then based on it, we proved our theorem, and then it turned out that this claimed theorem, they didn't actually know how to prove, so we also needed to prove the theorem. So it's somewhat of a funny situation. And then a few years later, I figured out there's like a one-page proof of this 10-page proof. Anyway. Yeah, so what this theorem says that if these vectors, they typically agree when you sample them like with some significant intersection, then they should really come from some global vector. Okay, and now, why do we expect this to be the case? So, given S1, then the distribution of S1 intersect S2 is, I think it's mu1 over square root 2, sorry, of S1. So it's kind of a random restriction of the S1 itself. Okay, so we know that typically GS1 is close to F restricted to S1, and so GS1 restricted to S1 restricted to S2 is close to F restricted to S1 S2. And also, the same thing, similarly, GS2 restricted to S1 restricted to S2 is close to same thing. Okay, so the idea is if you look at F and you first restrict to S1 and then to S1 intersect S2, it's the same as if you first restrict to S2 and then to the intersection of S1 and S2. Okay, so from this you can derive that the expectation over S1 and S3 coupled of the difference between GS1 restricted to S1 intersect S2 and GS2 restricted to S1 intersect S2 square with respect to, I think, mu1 over square root 2. So this is order epsilon. Okay, so I'm taking you some calculations, but this is the idea. So the idea is that typically these functions are close to restrictions of F, and when you look at these things, then these things are just close to the same restriction of F. And this is why they're typically close to one another. Okay, so I think maybe it's quite intuitive. But it's a really simple calculation, it's a bit confusing because we have several different measures floating around. Anyway, so we have this, and we want to prove this. Okay, and the idea is that if these two things are different, then this difference is order 1. Okay, and why is that? Because GS1 and GS2 are 1 juntas, so the difference is a 2 junta. So if the 2 junta is not 0, and it's also it's like 0 plus minus 1 value or something, so if it's not 0, then it's non-zero with some constant probability, and because it's integer value, then the norm squared will be lower bound by some constant. Okay, so because this GS1 and GS2 are not arbitrary, they're juntas, then this claim and this claim, they're really the same. Because if these two columns are different, then these two G functions are different, they differ by a lot. Okay, we say that they form a code. So all of the one juntas, they form a code. Any two functions are either the same or they're really very different in this norm. Okay, so we prove this, and we prove this, and now, if you believe the disagreement theorem, then it implies that you can construct this gamma and finish the proof. Okay, so since I believe I'm out of time, we're not going to do the proof of the agreement theorem now because everybody is already lost it. It's a bit bit late in the day. So we might do it tomorrow morning, first thing in the morning, before some of you even wake up. And then the plan is to discuss a bit generalization of this to the symmetric group. Okay. And afterwards, in the last talk, I'm hope to discuss degree D extensions. So this is the rough plan for the rest of the talks.